We want to predict energy output of a solar power plant based on the current weather conditions. And again, there can be various business implications why we want to do it, most notably preparing for a coming storm, other weather conditions, etc., etc. It is a regression problem. Response variable here is the energy output, which is output of the solar power plant in kilowatts. And because the output is continuous, therefore this is a regression problem. There will be 9 available predictors that indicate different things, like this is our response, energy in kilowatts, and our predictors will be related to the sun elevation, sun direction, temperature, precipitation, cloud cover, humidity, wind speed, the wind direction, barometric pressure at a specific hour of the day. As you can see in this snippet here, we start at 5 a.m., then look at 6 a.m., 7 a.m., and so on and so forth. So those are the different hourly windows of the power generation of our power plant. Okay, so this is the problem that we try to address here, and let's unleash TreeNet on it. And again, I'm going on the predictive analytics module, pick TreeNet regression this time. In this case, energy is our response variable. I use 9 predictors other than time, and then I pick validation with the test set at 30%. And I set simple options, 300 learning cycles, and actually 400 learning cycles, and 0.05 learning rate. So I click OK, and that allows me to see and view the resulting TreeNet model here. So let's have a detailed look at some parts of the output. So first of all, this chart here communicates how the amount of learning on both training and test samples increases as we keep on adding the learning stages. It also communicates the importance of variables according to their contribution into the model. The sun elevation is the top most important variable, which is not surprising. That's how high the sun is above the horizon, followed by all those others. When you look at the model performance, again, I'm interested in test performance, and it communicates 88% R squared on an independent 30% test sample. And if I compare what I see here with what I've obtained before, we will discover that CART regression tree managed to explain 82% of the variation in the power output of the power plant. A random forest reached 88% accuracy in terms of test R squared, even though it didn't give us any clues into how the variables contribute into that output, but it did give us a powerful model. And the same thing with TreeNet. In this case, TreeNet and Random Forest, they produce comparable performance, but on top of it, TreeNet also gives us the ability to understand what's going on by looking at TreeNet partial dependence plots. And again, I will just highlight a bunch. If you look at sun elevation, it is very clear that once the sun reaches higher levels in the sky, our power output increases dramatically. Similarly with sun direction, when the sun is towards the south, this power plant happened to be located in northern hemisphere, towards the south is associated with the highest levels of output. Similarly, cloud cover, as long as we have about half of the sky open, we are okay, otherwise the power output will drop. And similarly, precipitation. If there is no rain or very little rain, we are okay. But then, with some rain, the power output drops precipitously. As far as 3D graphs, very similar story can be seen by looking jointly at sun direction and sun elevation, from which it becomes very clear that towards the middle of the day, southern portions of the sky, when the sun is at its highest, we have the highest output of the energy for our solar power plant. So very intuitive example, but it's nice, and I encourage you to compare our insights from single cart or random forest just to see how all these pieces nicely fit together. So what would be the overall conclusion here? TreeNet allowed us to identify nonlinear regions of high power generation. And the TreeNet achieved the highest performance of 88% R squared on the test sample, which is comparable to what we achieved with random forest. But above and beyond the random forest, TreeNet model gave us powerful insights into the nature of dependencies by supplying these 2D and 3D partial dependence plots. Now, let's summarize random forest versus TreeNet. We looked at two examples, one classification, one regression. The common themes occur here. Recall that random forest was developed by Leo Bryman and Adele Cutler in early 2000s. It generates multiple large trees independently and in parallel. And it induces differences by sampling variables and observations from the original data, and makes final predictions by averaging or voting. It is slow and bulky, and it produces no plots and no interaction controls. Okay? In contrast, when you look at the TreeNet, the center point of discussion today, it uses incremental learning. It was developed by Jerome Friedman in early 2000s. It's actually kind of competing with random forest, both in time and space. It generates multiple small trees sequentially, okay? And each subsequent tree corrects the errors of the prior trees and makes final predictions by adding all corrections together. It is fast and efficient, and it produces partial dependence plots and interaction controls. Now you can see how these things compare to each other, complement each other, and compete with each other. The nice thing about random forest is that it can be fully parallelized. You can build it on multiple machines independently. As long as they run different random number seeds, you will be fine. TreeNet, on the other hand, requires sequential model construction. You have to wait for the first stage to finish in order for the next stage to start. But on the other hand, TreeNet gives you all of the efficiencies and the interpretations associated with it.